Okay, so last time we were discussing, so again, let me, so I want to remind you, just recollecting what we did previously. So I want to define what we mean by Cartesian tensors. And to aid that, I said that let's take specifically Euclidean space R3, that is our usual three-dimensional space. Then we can choose Cartesian axis in the following way. And also, as I said, I'm going to use this more sophisticated notation because this allows us to generalize to other kinds of situations easily. And in particular, okay, so this means that if I choose this set of three axes, so it's like I've chosen a set of bases vectors E1, E2, E3. And what we've said that if you have any other vector belonging to this space, then it can be written as a linear combination of this basis vectors. And these three real numbers, U1, U3, U2, U3, give a realization of the vector U with respect to this basis. Then what we said was that, or what I did was that, I said that suppose now I choose, since our choice of basis is not unique, now I choose another basis, B prime, C prime. Then what is the relation between these components with respect to basis B and B prime? And that we have figured out that given linear transformation, how we can relate the components. And specifically now, this particular vector space can be endowed because we can also define an inner product of this in the following way. So I define an inner product. And then I've made the choice of the basis now is that the basis vectors constitute an orthonormal basis. So this is this. And then what I said was that suppose we consider now a linear transformation R such that the inner product of any two vectors in this vector space is preserved. Then what we found is that the linear transformation R must be an orthogonal transformation which satisfies this relation. So I've written this in the form of a matrix, but we could as well have written it. I mean, we have the component versions I've written down earlier. Okay, and what this implies is that you have both a right inverse and a left inverse. Please remember this is transpose. Okay? So it tells me that R inverse is equal to R. See, because it's a transformation which takes you from one basis to another basis, R is invertible and complex. And this, by definition, is a definition of an orthogonal matrix or an orthogonal transformation. Okay, and just because I think there was somebody last time, one of you have mentioned that this is the definition of a unitary matrix. I want to very quickly tell you what is the difference between an orthogonal matrix and a unitary matrix. Because you will have reason to deal with both of these. So it's best to just see what's the difference. Remember that here, this is a real space. It's a real vector space, so all these are real numbers. So the matrix or the linear transformation which takes you from one basis B to the other basis B prime is also a real matrix. So in this case, your R is a 3 by 3 matrix. So all the 9 elements are real numbers. Now the definition of a unitary transformation or a unitary matrix, I'll just write it in the form of a matrix is the following: that U dagger equal to identity. So it's again a square matrix, but now your U is a complex matrix, complex valued matrix. Or in other words, what it means is that the elements of the matrix U are complex numbers. So for example, now if I had here a 3 by 3 matrix, there will be 9 real elements. On the other hand, if you have a 3 by 3 matrix U, then in that case, which a complex matrix, then in that case you have 18 real numbers because each element is complex, which means you can specify it by 2 real numbers. So therefore you'll have 18. So that's one thing. So it's a complex valued matrix. And U dagger by definition is U star transpose. So again, what this tells you is that U inverse equal to U dagger. So if you look at it, I mean, if I now say that I restrict myself here to only real matrices, then this actually just becomes this. This definition for a unitary matrix just becomes a definition for an orthogonal matrix. But it's useful to keep the distinction in mind and think of these as somewhat separate. Although, I mean, it's true that if I'm considering only real numbers or real valued matrices, because then your U star is the same as U, so it simply tells you U dagger is the same as U transpose, and U inverse is the same as U transpose. But still, I would request you to keep this distinction in mind. See, because from this, what we have seen is that this tells me that determinant of R square was 1. And because the distinction is the following. So this tells you that determinant of R is plus or minus 1. On the other hand, if I look at this, what this tells me is that determinant of U into determinant of U star equal to 1. Or in other words, modulus of determinant U whole square equal to 1. So what this therefore tells me is that determinant of U is equal to a phase. So it's not simply plus minus 1. So for an orthogonal matrix, this phi can only take either 0 or pi. For a unitary matrix, it will be more arbitrary. So that distinction one has to keep in mind. So just remember this, okay? Anyway, so this was simply a small digression from this thing. And you can also notice that here our ij is nothing but ei prime ej. Because if you remember, my ei prime was equal to rij ej. I'm now using the summation convention. I've also introduced the summation convention last time. So here you can see that j is a repeated index. So instead of writing j equal to 1 to 3 here, summation over j equal to 1 to 3, I just drop this. And because j is now a repeated subscript, which means I'm summing over this j. And on both sides, I have this free subscript I. And here you can simply see that this is this. All right. So again, I want to tell you that, make you note that Rij is a matrix which is relating to different basis vectors. And in our three-dimensional space, given that we have this relation, what we found is that your R is actually just specified by 3 real elements. So I really require only 3 real parameters to specify my rotation or to specify R. So what, and in particular what this is doing is that, the fact that I'm preserving the inner product, so because I said that this should be the same as U prime, V prime. So a rotation transformation is such that UV with respect to V is the same as UV with respect to V prime. So therefore, what it says is that, and if I now look at it from a pictorial way, what this rotation, why are we calling it a rotation transformation? So essentially, what it's doing is that I'm going from this basis, or I'm going from this axis to another axis, to another set of 3 axes. In other words, I'm just rotating my Cartesian axis. So this is my new E1 prime, E2 prime, E3. Because from here you can see this. That's all I'm doing. And why do I say that I'm just rotating? So I can imagine. So let me take for a particular case. Let's just take that I'm only doing the rotation about the. So I'm considering now I have the x-axis. So imagine that I have the x-axis, y-axis, and z-axis. I make now a transformation. A rigid rotation transformation where I keep my z-axis fixed, I don't do anything, but I change the x-axis and the y-axis. Or I rotate the x-axis and y-axis by some angle phi. So I have now this new x prime. And this is my new y axis. my z-axis is now, I mean, the way I've drawn here, the z-axis is coming out of the board, so that remains the same. This constitutes, for this rotation transformation, or in other words, that particular transformation constitutes a transformation which satisfies these conditions. How to check that? How will you check that this is really something which satisfies this condition? Specify now what exactly is your rotation matrix. Or in other words, what we can ask is that under this, what are the new basis vectors? So here I have written here E1, E2, E3. So your E1, E2, so this is like your X, Y, Z axis, E1, E2, E3, E1 prime, E2 prime, E3 prime. Now since my Z axis has remained the same, it means my E3 prime and E3 is the same. So these vectors are the same. So if you look at the matrix R, see we have these rows. Because R11, R12, R13, R21, R22, R23, and then I have R31, R32, and R3. So E3 prime is the same as E3. So what this tells me is that I have just, because it cannot mix up, E3 prime doesn't get mixed up with E1 and E2. So therefore these two elements must be 0. So I simply get on the last row, I simply get 0, 0, 1. For reference, just look at the definitions which I've written explicitly. E3 prime is equal to R31, R31 E1 plus R32 E2 plus R33 E3. But since it should be same as E3, I can only get 1, and I can only get 1 because my inner product must be preserved. Finally, also we can see that the X and the Y, they are not getting, or the X prime and the Y prime are not getting mixed up with the Z axis because the Z axis is remaining the same. So what this tells me is that this last column, this part should be 0. Fine. Then what is left here? So now I made a rotation. So I made a rotation. So this is my new basis vector, and you can see that R11 from here. You can see that your R11 must be equal to the inner product of X prime with X. Now X prime given like this, that I made this rotation with phi. X prime dot X, this vector dot X. What should I get here? Because this inner product is nothing but, if I think of it in the form of vectors, it's just this dot product between these two. So here I must get here R11 therefore should be the same as X prime X. And given this picture, what is X prime dot X cap? X cap prime dot X cap.
Cos phi.
It should simply be cos phi. And what will this be? That is R12, right? So that R12 should be then equal to X cap prime dot Y cap. So it means it should be, see, because this is cos phi, so what will this be? X cap Y cap.
Sin phi.
Sin. And then you use simply the orthogonality, or simply you can use this definition, and you can see simply that I'm going to get minus sin phi cos. So this is explicitly a realization of your one particular realization of your rotation matrix, or the matrix R. And you can check, it's obvious that this is an orthogonal matrix. It satisfies this relation. And in this case, okay, now we said that any matrix R must be specified by 3 real parameters. Now, so which are the 3 real parameters which is specifying this R? So one you can see is here already inside the definition itself, that I need a parameter phi, which is telling I am rotating it about the Z axis, or the angle by which I am rotating the XY in the XY plane. That is phi. So that's one parameter. And then the other thing I have to mention is the axis about which I'm doing the rotation. So here in this case, I'm saying that I'm doing the rotation about the Z axis. Or in other words, I have to specify the direction about which I'm doing the rotation. And to specify any arbitrary direction in 3-dimensional space, how many parameters will I require? Suppose I will just want to specify it. I don't need the magnitude of a vector. Imagine this, that I have some, let's say I have some R here. Okay. So if I want to specify the direction of this, the magnitude of this will be given by the modulus of R. What about the direction of R?
Theta and phi.
Unit vector.
Yeah, if I, yes, that's why I can use the theta phi, so I can figure out the angle which it makes with the z axis and then the azimuthal angle and the polar angle. So that theta and phi, or in other words, I require phi and the direction or the axis of rotation. And for any axis of rotation, I've used it as a unit vector because I'm just interested in to know the direction. I don't need the magnitude. And any axis of rotation is specified by two parameters. So these are the two real parameters, and then the angle or the amount of rotation which I'm doing. So that is one way to specify these three real parameters. This is called the axis angle way of parameterizing the rotation matrix. Please keep this in mind. One reason why I'm doing this a little bit elaborately now is that later on it will be easy for me when we go to group theory and we talk about rotation groups. So at that point we will be using all this information. Okay? So there are alternate ways of parameterizing. I mean, finally it is three real parameters. That number doesn't change, but whether I use an axis angle parameterization or some other way of parameterization, that will depend. Okay? That will depend upon convenience. So the other ways are using other angles and so on. So essentially what we are doing then is that the rotation transformation essentially corresponds to a rigid rotation of your Cartesian axis. I mean, one can show that any such rotation transformation, which is specified by, as I said, by three real parameters, constitutes a rigid rotation about some axis of rotation by an angle, some amount of rotation. Now, what we want to do is look at how quantities. So let me say what we are. Therefore, I am now going to consider that I have this Euclidean R3, this three-dimensional space, our usual three-dimensional space, specified by axis E1, E2, E3, Cartesian axis, and then I now consider transformations or rotation transformations. It will take you from this E1, E2, E3 to E1 prime, E2 prime, E3 prime, which is again the inner product of any two arbitrary vectors is preserved, and in particular it tells me then that the length of vectors is preserved and the angle between the vectors is also preserved. And now we want to examine how various quantities transform under such, or how various quantities behave under such transformations. Already we have seen last time that if I have, so by definition here you've seen that if I have the scalar product, then with respect to B and with respect to B prime, it's the same. This is by definition. So my scalar product or the inner product doesn't change under this transformation. On the other hand, what we have seen is that if I have a vector, then the components of the vector with respect to the two bases are given by this relation. Again, I'm using the summation convention here. So what this tells me is now if I have a set of vectors, which means essentially I have a set of three quantities, U1, U2, U3, then under a rotation transformation, these components change. So this goes to, so this is with respect to B and this is with respect to B prime. And U1 prime now is a linear combination of these U1, U2, U3. That's what this is telling you, but it's not some arbitrary linear combination, but it has to transform exactly like this in terms of your rotation matrix R. Similarly, U2 prime will go this way. Further, we also saw that we have other quantities. So if I take a linear operator A, then we saw that that transforms again in a different way. So in other words, what we find now is that under this rotation transformation, I can get quantities transforming. So these quantities in the two different bases will depend upon what choice I made of the basis. Sometimes they don't depend, like here, but here you can see that it makes a difference which basis I'm using. And also the transformation properties have somewhat are definite. That means it will depend upon what R I have chosen. So now what we will do is, I'm going to now into a different way of defining now vectors and scalars. We will use these transformation properties now. So this is now yet another way of specifying what we mean by a vector or a scalar. And in particular, I'm talking of Cartesian scalars and Cartesian vectors. So I'm now going to say that consider a set of, say, three quantities, some arbitrary set of three quantities, V1, V2, V3, real quantities. Okay. And if we find that these three real quantities, so these three real quantities I've chosen with respect to basis B. And if we find that they transform with respect to, so when I'm writing this component form now, if we find that in the basis B prime, so I find out what they are with respect to basis B prime. And if I find that the components are transforming like this, if you find this, then I will say that these set of three quantities constitute a vector or a Cartesian vector. Or more generally, I will say that this set of three quantities constitute a Cartesian tensor of rank 1. Or sometimes it's called a rank or order 1 Cartesian tensor. Okay, so there people write it as rank 1 or first order Cartesian tensor. Or in other words, but this you can see is nothing but how a vector transforms. So our usual vector is really nothing but a Cartesian tensor of rank 1 or a first order Cartesian tensor. So this is by definition now, that if I can find a set of three quantities like this with respect to a basis B, and if the transformation properties under a rotation transformation, rigid rotation transformations are this, then in that case I will call these V1, V2, V3 as a Cartesian tensor of rank 1 or first order Cartesian tensor. Then I will define now a scalar as a quantity which does not change under rotations, or scalar or a zero rank tensor. So what we were calling as a scalar, now we will call it as a zero rank tensor or a zero order. So sometimes instead of rank, people call it a zero order. In some books you'll find this. A zero order tensor is a quantity which does not, again I'm referring all of these to Cartesian tensors, which means I've chosen Cartesian basis, or Cartesian axis, is a quantity which does not change under rotations. So the example for this is of course our scalar product or the inner product. Yes. Okay. Do we have an example of a first order tensor or a first order vector? So the most obvious example is of course our position vector itself. So if I go to R3, my three-dimensional space, if I look at this, the position vector R, then you know that the components are x1, x2, x3 with respect to say basis B. Now with respect to E1, E2, E3. So my R, I can write it as equal to x1 E1 plus x2 E2. This is my position vector, our usual position vector, plus x3 E3. Where x1, x2, x3 are the components along the E1, E2, and E3 axis. E1 Okay. Now, if I go to the basis B, B prime, or with respect to this E1 prime, E2 prime, E3 prime, then in that case, what will be the coordinates? It will become x1 prime, x2 prime, and x3 prime of the components. Okay. So the same thing can be written as x1 prime, E1 prime, plus x2 prime e2 prime plus x3 prime e3 prime. And just as we saw earlier, after all, this is, you know that this is a vector in my R3, and we already seen how this changes. So your x1 prime, x2 prime, x3 prime, and I don't have to do again separately, but my xi prime equal to Rij. Again, I've used the summation convention here. Fine. So therefore, your x1, x2, x3 constitute a vector dimensional space. Now, let's consider this combination instead of this. Suppose I consider this combination. See, please remember here I'm just specifying a set of three quantities, and what you want to check is whether that set of three quantities constitute a vector or not. So if I just specify you now for three real numbers, x1, x2, x3, where x1, x2, x3 are the components of this position vector along x1, x2, and x3 axis, then in that case, it's trivial or obvious that it transforms into the components of vector. But instead, if I take this component, this combination, let's consider like this: x2, x1, x3. Okay. So let's take this combination. Again, where x2, x1, x3 are this, basically I've taken this position vector and taken these components and put it in that form. Okay, put it in this order. Let's check whether this U constitutes a Cartesian tensor, rank 1 Cartesian tensor or not. And for simplicity, what I'm going to do is let's consider the rotation transformation, which I took explicitly just now. So let's take this R to be equal to this cos phi sin phi 0 minus sin phi cos phi 0, 0, 0. So let's consider this particular transformation, rotation transformation. Basically, I just rotated about the z axis by an angle phi. And I want to now check whether this set of three quantities constitutes a rank 1 Cartesian tensor or not. Okay. All I need to check is whether, now in this case, what is my U1? So please remember that U1 is equal to x2 here, U2 is x1, and U3 equal to x. So if I can show that Ui prime equal to Rij Uj, then I'm done. Okay. So I want to find out what is U1 prime, U2 prime, and U3. Now you can see that what is U3 prime? U3 prime will be nothing but x3 prime, because my U prime, according to this definition, U prime should be equal to x2 prime, x1 prime, and x3 prime by definition. Because I've just taken the position vector and interchanged the first two components. That's all I've done in defining U. So in the new basis, it should be that I interchange the other the prime x prime and y prime components. So it should be x2 prime, x1 prime, x3. Fine. So what this tells me then is that U3 prime is nothing but x prime, which is equal to x from here. Okay, which is equal to U. What about U2 prime? U2 prime is nothing, or let's start with, let's start with U2 prime. U2 prime is x1 prime. But from our usual way of, how the position vector transforms, what is x1 prime under this transformation? Under this particular rotation transformation? The position vector will transform like this: xi prime equal to Rij x3. So what will be x1 prime? See, this will tell me that x1 prime should be the same as R1j xj. Correct? From here, I is the same. But what is R1j xj? So this tells me that this should be equal to R11 x1 plus R12 x2 plus R13 x3. But R13 is same as 0, so I don't have an x3, because that we know that I'm not going to mix up this. So this is 0. But what is R11? R11 is cos phi, R12 is sin phi. So I simply am going to get cos phi x1 plus sin phi x2. Alright. Similarly, what I'm going to get is for x2 prime, I'm going to get minus sin phi x1 plus cos phi x2. So let's therefore substitute here. U2 prime is x1 prime. So I can write this as cos phi x1 plus sin phi x2. Fine. But this I will write it now as cos phi times x1 is nothing but u2 plus sin phi times u1. So u2 prime is cos phi u2 plus sin phi u1. Fine. On the other hand, or if I go ahead now, u1 prime now. U1 prime is nothing but from this definition, it's x2 prime. And x2 prime from here we can see is nothing but minus sin phi times x1 plus cos phi times x2. But according to us, this will become minus sin phi. Now x1 is nothing but u2 plus cos phi times u1 because x2 is this. So if I take all these into account, what I will find is that u1 prime, u2 prime, u3 prime become equal to sin phi cos phi 0. Then I'm going to get here u1 prime cos minus 1. So it's cos phi. So from here u1 prime is this, so minus sin phi 0. Then I'm going to for u2 prime and this sin phi cos 0, 0, 0. This is what I mean. So what this tells me is that, what does this tell you? Do these three quantities constitute a Cartesian tensor of rank 1 or not? Remember, this was our rotation matrix. So do I get this relation between the things? I mean, if I should get, remember, I must get this relation that ui prime should be equal to rij uj. So ui prime equal to rij uj. Is this satisfied for this set of three quantities, given that I have this explicit realization? Anybody? It's a mistake here. Is this satisfied, this relation? Given that I have the transformation laws like this, I mean, I explicitly figured out what is a transformation. See, for that, all I have to check is whether this matrix is the same, because that means that I should just simply get x1 prime, x2 prime, x3 prime equal to r times x1, x2, x3. But is this the same as r?
This is R transpose.
So it means it is not the same as r. So therefore is x2, x1. So if I put the order of these three elements like this, does this constitute a Cartesian tensor of rank 1? By definition. It doesn't satisfy, right? So therefore this is not a vector. Or it's not a rank 1 tensor. On the other hand, consider this quantity. Suppose I take this. I will suggest that you people go through these examples afterwards, go back and look at them carefully and think about it a little bit. Consider this one now. X2 minus x1, x3. Suppose I take this, the quantities I choose like this. X2 with minus x1, x3. So that means your V1 is the same as x2, V2 is minus x1, and V3 equal to x3. Again, find out what is V1 prime, V2 prime, and V3 prime. So your V1 prime by definition will be x2 prime, because if this is So your v prime will go to x2 prime minus x1 prime and x3 prime. Okay. Okay, I'm giving this as an exercise now. Show that this constitutes a vector. Verify now that this particular combination. So if I write it as x2 minus x1 x3, then this will be a vector. On the other hand, x2 x1 x3, that set of three elements. So remember the order matters. So x1 x2 x3, that constitutes a vector. But x2 x1 x3, if I put those elements in that order, that doesn't constitute a vector or a Cartesian tensor or triangle. But if I take on the other hand x2 minus x1 x3, that constitutes a vector. So verify this. And the verification you do exactly the way I have done. Okay. So all you need to show now is that vi prime is the same as rij bj. And use the transformation properties of x1, x2, x3, which is this. And again, you can take this specific rotation transformation. So under this rotation transformation, this set of three quantities do not constitute a vector, while this set of three quantities constitute a vector. Again, this set of three vector quantities constitute a vector or a Cartesian tensor of vector. So the purpose of this whole exercise is to tell you that this is not completely trivial. I mean, you might think that, okay, what is so great about it? That, I mean, okay, we know like x1, x2, x3, we know that it transforms. So any three quantities constitute a vector, so that is wrong. Any set of arbitrarily, I cannot have any arbitrary three quantities. And if I just put them together, that will not transform like the three components of a vector or the way we want it. Okay? So, or in other words, what it tells me is that this transformation law is very specific. It's not like that any set of three quantities can satisfy that kind of transformation laws. So it's kind of restrictive. So only certain sets of quantities can behave like a vector or will transform like a rank 1 Cartesian vector. Okay. So that's what you have to learn from this. And again, I want to urge you people that please go through this example which I've solved explicitly and do this exercise, because I think that will help you to understand the concepts well. It's not very difficult, but just go through it. Okay. So now we have some examples. So our position vector, okay, let me go back. So we had an example for rank 1 or a first order tensor. So this is a position vector R. Standard one, x1, x2, x3. Okay. And then we saw that if I change the orders, it makes a difference. It need not necessarily, those set of three quantities don't necessarily be the components of a vector. Now, given this position vector R, if I take R dot R, then this is going to become x1 square plus x2 square plus x3 square. Now, this quantity is, how will this transform under rotation transformations? Under this rigid rotation transformation which we are talking about, how will this transform? In the new basis, what should this be?
It will not transform. It will be invariant.
So because it's going to become r prime dot r prime, so it is simply going to become x1 prime square plus x2 prime. Or in other words, your x1 square plus x2 square plus x3 square is the same as x1 prime square plus x2 prime square plus x3 prime square, given that we have made the transformation a rigid rotation transformation. Okay, the length of the vector doesn't change. So therefore, this quantity r dot r. So given this position vector r, I could make this quantity r dot r, and that transforms then like a zeroth order tensor or a scalar. Okay. So then I can ask now, can I construct an object which transforms differently from both scalars and vectors? So let's see if we can do that. And what we will find is that it is possible to do that. And now I'm first going to give a definition, or maybe I can introduce it to an example. Consider this object. See, this is something which we construct. This we call as the inner product, right? Because it's really nothing but the inner product of the position vectors, if I think about it this way. So I took two vectors and made that from the two vectors I made one number. Now instead of that, let us say that I make this quantity xi xj. Consider this quantity. How many sets of elements will this be, xi, xj? How many such quantities can I construct? Xi are the components of this position vector, x1, x2, x3. And xj is
Nine.
also 9, right? Because x1 square, x1, x2, and so on. So I can get 9. And let me call this as some Pij. Let's instead of calling it Aij. So I have 9 such quantities here, Aij. This is with respect to the basis B. Now with respect to the basis B prime, I will get A with respect to B prime. By definition, it is simply x prime, xj prime, xi prime, xj prime. Okay, so again let me. So I hope you understand now what I mean by this A prime. So in this basis B prime, it's given by x prime, xi prime, xj prime. Now, is there any relation between these? Let's see if we can find them. We already know what is the relation between xi prime and xi's because of the fact that these are the components of a position vector. So I know that xi prime equal to rij xj. So I can see that I can write this now, xi prime as ri. Okay, now already I have here a free index j. And you can see when I wrote xi prime, I wrote it as rij xj. But so I want to write that in terms of this xj, but I will use now, instead of using j, I use this or ij xk here. And 1 second. So let me just write it first. I do not use again j here because if I use j, then this will no longer be okay. So I want to demonstrate this because students, even after a lot of experience, make this mistake. That's why I'm emphasizing this. This is not equal to rij xj xj prime because this is such a state, such an expression will not make any sense because here j is a repeated index. And this kind of 3 indices doesn't make any sense. And finally, here I will not get the free index j here if I have such a repeated index. So whenever I have such expressions, you use another dummy index here. So for xi prime, I used rik xk. Again for xj prime, I will use another. I'll write this as rjl xk. Okay. So I'm going to therefore get here now rik rjl xk xs. And this I can write it as equal to rik rjl, but xk xl is nothing but this, so I can write this as akl. Or in other words, what I find is that my aij prime equal to this. Okay, again I want to see just to understand this dummy indices and so on. So ij here are free indices or free subscripts. K is a dummy subscript, and you can see that the second subscript of this R is getting summed over from this first subscript of A, and here the second one of R, and the next one is getting summed over with the second subscript of. So what we find is that now if I look at this quantity xi xj, these 9 elements, then they don't transform either like a scalar nor like a vector, but they have again definite transformation properties, because again you can see that the values depend upon which basis you're using, but they transform differently and they have this definite transformation properties, which again will depend upon your rotation index. So in other words, what this tells me is that I can construct now, I mean, I explicitly here what I did was I constructed two quantities from our vectors, which had now again definite transformation properties of the rotation transformation, which was this, right? And this is actually called what is called as an outer product of the vectors. So this is really, this was an inner product, give you one number by multiplying in quotes. If I multiply two vectors in quotes, then I can get what is called as the outer product, which gives you a set of 9 elements, and you can see that this transforms like this. So this tells me therefore that I can actually construct objects which are having transformation properties which seem to be generalizing that of our vectors. Because for the vector we found one R, for the scalar there was no R. Now in this quantity I have two R's coming into picture, but you can see the summations are specific. So we can imagine that what I should call this. So I have two R's, now I'm going to say that I'm going to call this as a something which transforms like this. I'm going to now say it's called a Cartesian tensor of rank 2. Okay, or more generally, let me give you a definition now. I gave you before I gave the definition, I gave you a demonstration of an example, but now I'm going to say that we can define a Cartesian tensor of rank 2 as something of rank 2 or order 2 as something which has two indices. See, vector had vi prime. So it's a set of 9 elements. For the vector, we had v1, v2, v3. So I had one index there, one subscript. Here I have now 9 elements. So I have two subscripts, ij. And the transformation properties of these with respect to the two bases should be the following. So I have a set of, so Tij is a Cartesian tensor of rank 2 if T prime ij is IQ. So if the transformation properties are like this of these 9 elements, please remember that just like for the vector under a rotation transformation, the three components get mixed up under the rotation transformation. Now for a tensor, second rank tensor, which is Tij means I have 9 elements. Those 9 elements get mixed up under this rotation transformation, and they should get mixed up like this. Then I will call this as a Cartesian tensor of rank 2 or a second order Cartesian tensor. Now you can imagine that I can generalize this definition to higher orders. So for a higher order tensor, so now I can now say a tensor of rank 3. How many indices should that have? Second order tensor had 2 indices or 2 subscripts. Tensor of rank 3, how much should it have? What would you expect? 3, right? So now let me give it the label like this: Ti1, I2, I3. So how many elements will this have in our 3-dimensional space?
27.
Yes, 3 into 3 into 3. So it will be 27. And if, so I will write like this. So Ti1, I2, I3 is a tensor of rank 3 if under the rotation transformation so now I will require 3 R's. And again, you can see that the first indices in each of these R's is a pre-index. The second subscript in each of the R's is a dummy subscript or a dummy index, which is getting summed over with these keys. So if the 27 elements of this object get mixed up under rotation transformations in this fashion, then in that case, I will call this T as a tensor of rank. And again, I want to say that just like I demonstrated for you, it is not that I can put any arbitrary 3 quantities and say that they will form a vector. Like we saw that explicitly. If I have x1, x2, x3, that will transform like a vector. On the other hand, x2, x1, x3 is not a vector. So in the same way, it's not that any 9 elements will have this kind of transformation properties, or any set of 27 elements will have these transformation properties. They will, if the transformation properties like this must exist, then you will have only very definite kind of combinations which will be allowed. And more generally, now I've talked of the third rank tensor, and more generally now we can talk of a mth rank tensor. So I'm going to define now a tensor of rank m. So I can talk of Ti1, I2, Im, because is a Cartesian tensor, I must require m indices of rank n. So most generally then, I can define a Cartesian tensor of rank m or order n as something which has m indices. So how many components does this have? An mth rank tensor or this kind of an object.
3
to
raised
the
to
power
n.
n.
Pardon, 3 to the power of m. Okay, so you have these 3 power m components. Okay, and if the 3 power m components transform in this fashion under a rotation, under rigid rotations, then I will call these set of 3 to the power of m components as constituting a tensor, Cartesian tensor of rank n. Right? So this is our most general definition for a Cartesian tensor. So if it is rank 0, then it means that there is no index here at all. That's what happened for the scalar body. There was no free index at all, and it's just one number. If it is rank 1, then I will have one index, which tells me that it has 3 components. If it is rank 2, then there will be 2 indices, there will be 3 squares, so 9 components. Rank 3, 3 into 3 into 3, 27, and so on. Right? So this is something. Now, given that I've already shown you that how I can construct it. Because we have seen that given the position vector, I could construct x dot x, that became a scalar. I had xi itself, that's my vector, or x itself. Then I could construct this object xi, xj, this transformed like the 9 components of a tensor of rank 2. And it's possible actually now to construct even higher order tensors like this in the same xi, xj, xk, and so on. So what this tells me is that given vectors, given a vector, just a Cartesian tensor of rank 1, I can go to a lower order rank tensor. That means a tensor of rank 0 by constructing this inner product. I can also go to higher order tensors by constructing what are known as outer products. So given therefore vectors, it's possible, or given a tensor of a particular rank, it's possible for me to do some operations and go to a tensor of lower rank. And given tensors of a certain rank, it's possible for me to do certain operations and go to tensors of higher rank. What other things can I do? Tensors. Giving 2 vectors, we know that suppose I give you 2 vectors, u and v. See, you can see that I'm changing my notations as and when I please. But all of these are synonymous because sometimes I will put the vector bar and have some tangent moments. So my u, v now are 2 arbitrary vectors belonging to R. You know that I can add these 2 vectors. So I can consider this vector u plus v. Essentially, it will mean that if I have component form, it means that if I have u1, u2, u3, this with any basis, v1, v2, v3. Then u plus v will be nothing but u1 plus v1, u2 plus v2, and u3 plus v. By definition. Now, if u is a vector, v is a vector, or now in our more sophisticated language, u and v are tensors, rank 1 tensors. What about u plus v? Does this also constitute a tensor or a rank 1 tensor or not? What do you think? Does this constitute a rank 1 tensor? Okay, forget about tensor for a minute. Suppose I have 2 vectors. What u plus v, is it a vector or not? MMP to MMP1, given two vectors in the vector space. U plus V is again a vector or not a vector?
Yes.
Okay. So you know that if U and V are two vectors, then U plus V is also a vector. Okay. Now in this sophisticated language, then what do you expect this U plus V to transform as? If U is transforming like a tensor of rank 1, V is transforming as a tensor of rank 1, then U plus V should transform as? How would it transform as?
Tensor of rank 1.
It should also transform as a tensor of rank 1. Because after all, it's going to be a vector. And we have seen that by definition, a vector transforms or vector is nothing but a rank 1 tensor. Alright. Okay, so you verify this for yourself because now your next class is going to happen. Alright, so just verify this. And also please do that other, I'm not giving you more exercises because I want you to work out especially those two examples, x2, x1, x3 and x2 minus x1, x3. Use the rotation transformation which I wrote down explicitly and show that the first one does not, worked it out explicitly, but I want every one of you to work that out for yourself. Show that the first ordering does not constitute a vector while the second one constitutes that of a vector. Okay, so I'll continue with this tomorrow at the same time. Stop recording कुछ करना पड़ेगा इधर है ना stop recording
हाँ stop recording
इधर
हाँ उसको click